Lab 2, motion of a falling object. Let's get started. When an object falls, it has two main forces acting on it. One is weight, which is mass times gravitational constant, or 9.81 meters per second squared, multiplied by negative j hat. And j is just the y-axis. Drag is the other one, and it is negative b, and b is a resistance constant, and it's related to the size and shape of the object, multiplied by the vector v. Today, though, we are using turbulent drag, which is negative b times velocity squared. Here's the video. I wanted to use an object that had a lot of drag, or would have a lot of exact drag and a resistance as it tried to travel through the air, so it would be clear later on. The starting velocity, position, and time were all 0, and the mass was 0.024 kilograms. This was more of an estimate because I don't have any sensitive equipment to actually measure that. I took some information from online and made some strategic guesses. The experiment continues for just over a second. The delta t is 0.01 seconds, and that's the same for 59 frames per second. Okay, so here's the tracked footage. You can see that the origin is right where the cup starts, and you can notice that the y-axis is slanted because that's the way the screen is, so the cup falls down pretty well. Okay, and over on the right side you can see the graph. It's kind of sloped down. It sort of evens out towards the end though. Here's all the data from 0 to 1.03 seconds. Alright, I'd like to point out right here, the axis you can see on the screen, that was my measure of, that was my calibration stick. It's 1 meter from there to there. Okay, so moving on. Here's the code. Right, so right here the mass is 0.024 kilograms, as I said before, and this position and time, everything is 0. The delta t is 0.017, and here's the j hat, 1, the y direction, g is 9.8, and I'm keeping b 0 right now, so there's no drag. This is the non-drag. So this is how long it goes for time, and notice right here that w is equal to negative ball times gravity times j hat. This is the equation for weight earlier on, and same for the drag force that's here. And in order to find F net, it's weight times the force of drag. Okay, so standard ball velocity right here, ball position. We also included arrows this time to represent the force of drag and the weight. You'll see that when I actually open up or run the module. So right here, running it. Okay, and you can see the yellow is weight, and it's going down. It's going to continue all the way down past the end of the screen. And you can see it's accelerating quite quickly over here. Now we're going to go to the model with drag. Now we're going to have to include the b constant now. It's 0.035. Now when we run the simulation, you can see that there's a blue arrow appearing right here. It's the drag force. And look at the graph over here. It's a lot flatter towards the end. It doesn't accelerate as much towards the end. So now we're going on to the next page. Here's all the data. If you want, you can pause the video and peruse through it all, but I'm not really sure why you want to do that. Anyway, notice that the model with drag and the actual position are pretty close towards the end. It's just about 2% error, while the model without drag is quite far off. It's 2.5 times either of the other two end values, so very far off. Here's the graph. As you can see, the actual position and the model with drag are pretty close, although there's a little bit of a discrepancy between 0.25 seconds and 0.75 seconds. That might be due to the estimation in mass, which turned out to be important later. As you can see, the model without drag is way off. It's not a very good estimation. So yeah, the error probably has something to do with estimation in mass, which led to improper proportionality constant v. So that it was sort of a domino effect, I think, which led to a little bit of a discrepancy there. But it is still pretty close, which is good. Now, what does it mean? Oh, what does it mean section? Well, of the two models, the only one that you could predict the terminal velocity was the one with drag, because the one without drag would just continue to accelerate because the force on the object is non-zero. But the one with drag, you can actually determine the terminal velocity because it became, towards the end, the net force sort of became 0 because drag began to be equal to the gravitational force. And we found that the terminal velocity was about 2.6 meters per second. Now, here's an example if you were to throw it down at the beginning. Now, if we were to change the original velocity from 0 to negative 15 meters per second, we would get quite an interesting result. So let's run the module. Now, as you see, the graph kind of turns up. It starts off going faster, and then it slows down, which is kind of weird. But this is because the drag force is actually greater than the gravitational force, so it needs to slow down the object to its terminal velocity, as opposed to speeding it up to its terminal velocity. So this straight line right here would be the object's terminal velocity. Pretty weird. But anyway, that's the end of my presentation. Thank you for watching.